All right, thanks. This was really work that was primarily done by Shuai, but unfortunately he wasn't able to get a visa from the Canadian government to come and present this, so I apologize for any errors that I've introduced into Shuai's slides. Let's see. What's going on here? Oh, okay. Also, thank you for sticking through to the end of the talk. I know, or the end of the conference. I know, since we're in Canada, if this was your brain when you came, I'm sure it's kind of warm and melty like this now. Okay. So, all right. So, let's talk about these website fingerprinting attack papers. We've seen an excellent example of one 3 talks earlier. Right. So in the typical paper, we have this experiment where we download a whole bunch of websites a whole bunch of times through Tor, and from each of these downloads we extract some kind of feature vector, and then we feed that feature vector into a classifier, and that classifier, train a classifier that can tell us, this feature vector looks like it came from this website as opposed to those other websites. Right, so this is some rule for telling apart feature vectors from one website from feature vectors from another website or other websites. And so what are some kind of limitations of these of this way of looking at fingerprinting or website fingerprinting if we want to understand how the impact of the attack? Well, if we want to understand how bad is website fingerprinting, one of these papers is vulnerable. We're vulnerable to what features did we choose to train our classifier on, and which classifier did we use, right? And we just saw that if you choose a better classifier, you can get better results. It makes the attack look worse. Maybe if you use different features, we would have got even better results from our network, etc. The thing that we get out is not really a fingerprint of a website, right? It's a rule for telling that website apart from the other websites in our data set. So it depends on the other website. There's questions like one of the questions in the first after the first talk was how do these things scale? Can I tell apart? So PyUp showed us we could tell apart 100 websites. Can I tell apart 1,000 websites? Can I tell apart 1,000,000 websites? Can I tell apart 2 to the 32 websites? I don't know. There's no obvious way when you're using a classifier to incorporate auxiliary information that an adversary might have, right? If I'm in different parts of the world, I might be observing different kinds of traffic that people are trying to, or I might have different ideas about what kind of traffic if I'm an adversary, I might have different ideas about what kind of traffic my victims are sending over Tor. And, things like, because of that, these metrics that we use to measure how well the classifier does at telling apart monitored from non-monitored websites or website A from website B might actually be sort of underselling the attack effectiveness. Sort of like when PyUp went from looking at the top website to the top 2 against walkie-talkie, that thing, right? We saw that it was almost always putting the website into the right bucket of 2, right? Okay, so 3 years ago when Shuai started getting interested, was looking for another project, I said, here are some weird things about website fingerprinting. Maybe you should work on them. He came back with this really cool idea which is instead of thinking about websites in terms of classification, why don't we try to model website fingerprints by their probability density functions? So look at a whole bunch of traces, network traces from downloads over, say, Tor or not Tor. In this paper, we looked at Tor. And try to figure out, okay, what is the probability when I download google.com or google.ca that I see a particular feature vector, right? Or what is, maybe it's 0.1 when I see this one, or maybe it's 0.2 that I see this other feature vector, or maybe it's 10 to the negative 20 that I see this third feature vector, right? Okay, and so once you have this way of looking at website fingerprints, you can use it to study some of these other questions, or some of these other questions about website fingerprinting. So it's kind of backwards because actually Shuai was interested in the question, the scaling question, and he came up with this thing, and you could do it for a lot of other stuff, but whatever. So so this is a really cool idea, I think, that Shuai came up with, which is to model these website fingerprints with their probability density functions. And so Shuai came up with this method of sort of estimating or modeling fingerprint density functions. We call it WeftD, the website fingerprint density estimator. And in our paper, we sort of did one or two example applications. So the first one was once you've got these models that assign probabilities to feature vectors, you can use sort of information theoretic tools to think about website fingerprints. And so one of the things he did is he looked at measuring how much information a particular feature or a particular set of features gives you about a website. And that can be a potentially more interesting measure of how website fingerprinting attacks might scale. And also can capture more information about website fingerprinting defenses. And he also then conducted sort of a large-scale information leakage measurement of website fingerprinting features and defenses. So he, at the time, 2015 or 2016, went through all the literature on Tor website fingerprinting attacks and extracted a list of 3,000 different features that at least one paper had used to try to classify Tor traces, and extracted those from a large data set of Tor web browsing visits that he collected using the Tor browser crawler, and then measured how much information is in all these different features, how do they compose, which are more revealing, and so on. And then he also evaluated 6 different website fingerprinting defenses and showed that there are sometimes substantial gaps in what you might call the accuracy of a classifier and the information leakage of the accuracy of a classifier trained on this defense and the information leakage of the fingerprint vectors that the defense creates. So here's an overview of the WeftD system. So it starts with a set of website fingerprint feature vectors, and the first thing that WeftD does is it sort of extracts these features, and it computes mutual information among all the pairs of features to try to find out which features are highly correlated, essentially. And then it does some kind of clustering on the features. And then it uses that to further train its model. And then once you've got these models, you sort of sample from those models to compute information leakage about various features or defenses. So what were some of the things that, or some of the problems that Shuai solved to build WeftD? So one challenge is, okay, what's a good way to model these density functions for website fingerprinting or website fingerprint vectors? And there are a few different things to think about. So one is that these different features can have kind of different density spaces. So some features might be sort of more or less continuous. They vary over a wide range. Some features can be what Shuai calls discrete, where they're kind of, their density vectors are, or their density functions are point masses. And some can have sort of combinations. Like if you look at some website fingerprint defenses, they enforce that you either see something that's, say, 1,000 or less, or that's exactly 1,000 or 2,000 or more, something like that. And so he had to come up with a way to model these different kinds of possible density functions. And the other core issue is, of course, how to capture the fact that sometimes features can be highly correlated, and sometimes they might not be correlated. And the other challenge, of course, is the curse of dimensionality. If you want to estimate a good density function for something that has potentially 3,000 dimensions, you actually need, I don't know, exponential of 3,000 samples, and we didn't have that many. So how did Shuai solve this problem? So the first problem, sort of what kind of form of density functions to use, was this. Shuai used this thing called adaptive kernel density estimation. It's a non-parametric method that estimates the random variable's probability density function. And so basically you sort of take every point in your input and you sort of fit a Gaussian around it. And if 2 points are close together, you kind of merge them into a wider Gaussian, and you can sort of vary the bandwidth of the Gaussian around these points. It's called the bandwidth. There's this thing called there's a modification of this algorithm called adaptive bandwidth selection. And if you use a really narrow bandwidth, you can sort of approximate a point mass. If you use a really wide bandwidth, you can approximate these more continuous functions. And there are multivariate extensions of AKDE, which is obviously what we had to use for our 3,000 dimensional vectors. And the second thing, again, that the second approach or the problem that Shuai had to solve was this curse of dimensionality. And so for that, he used this thing which we found out later is called Kononex algorithm. So you take all your features, you compute, you sort of cluster them based on how dependent they are. Okay, and you say that if two clusters are sort of independent or not very dependent, then we can model them like naive Bayes. We can just multiply their density functions together. And so you can then train you can train kernels on the sort of sets independently. And the other thing is that if you find features whose mutual information is really high, you just take the one that sort of looks the best for the data that you have and throw the other one out. So your clusters get smaller. All right. So again, I manually surveyed the literature and found this list of 3,000 features that people had used up through 2016. He didn't use neural network extracted features. That would have, I guess, been an infinite list. And he downloaded for his closed world experiments the Alexa 100 web pages many times. He wound up with, after throwing out, hangups and whatever, 55,000 instances of those sites collected in 20 different batches. And he used a set of 100 websites for his monitored websites for the OpenWorld setting, and got 17,000, almost 18,000 instances of those in 8 batches. And the Alexa Top 2000 for the non-monitored sites in 10 batches, totaling 137,000 instances. That sounds like a small non-monitored set. Oh, wow, I'm almost out of time. But I guess I won't talk about that later. So the first thing he did was he built his WeftD fingerprints for the 100 monitored sets, or the 100 monitored sites, and he clustered the. He took the 183 features which had the most information about which website they were from, and clustered those. Found 13 clusters, 14 clusters. Some interesting results about that is that many of the features found in different papers were essentially completely redundant, so they were perfectly correlated to other features, so you didn't really need to use them both. The clusters that he got out of this clustering often grouped features from different papers into similar sets for the AKDE. Then once he had these, once he had these clustered features, he computed the information contained in all of them. I think this might actually be the total set, not just the 100 or whatever that were left over after throwing out the redundant features. And then this is just the sort of count of how many bits of information each of the features contain. So you can see that 2% of the 3,000 features, which is like, 60, had over 3 bits of information about what website you downloaded. So this is like a single feature bit, or a single feature component. And nearly half leak at least 1 bit. So there is, in fact, a lot of information present in these website fingerprint features. So you might expect them to be able to scale to much larger monitored or closed world sites. This is just the information. The information about the website from each of the Alexa top 100, top 500, or top 1,000 websites in all of the 3,000 features. This is if you aggregate the features instead of looking at them individually, how much information the feature sets have. And this is with a closed world set of size 100. So the maximum number of bits is, oh no, this is not 100. It must be 1,000, since things are going over 7. He also did a sort of open world measurement, And in this case, the OpenWorld, there were 100 monitored pages, and the non-monitored set was either the Alexa top 500, top 1000, or top 2000. And you can see that as the size of the closed world, as the size of the non-monitored set increased, the sort of amount of information that these feature sets provided decreased, but it sort of slowed down. And there's another graph in the paper where we show that it sort of stabilized a little bit under 2000. The other thing that Shuai looked at was how accuracy is not necessarily the best way to judge a website fingerprinting defense. So here he simulated a whole bunch of different website fingerprinting defenses, and for each of them, he trained a KNN classifier using the total 3043 dimensional feature vector to get the accuracy. And then he also figured out how much information was about a website was present in those feature vectors using WeftD. And you can see that some of these defenses that might look good by accuracy, like a WTF pad up in that right-hand corner, still leak quite a bit of information about what the website in question is, which was also illustrated by an earlier talk. Others didn't. All right, thanks. Shuai wanted to thank a lot of people for helpful discussions about this work. And if you want to produce website fingerprint density estimations of your own feature vectors, you can get Shuai's code for doing that at this URL down here.
Hi, I'm kind of curious why you chose mutual information. I mean, for one, this requires you to have a prior distribution, which I guess would be representing the adversary's prior knowledge. So I'm not sure where you're going to get that.
I'm sorry, what do you mean by mutual information? At which step in the process are you curious about mutual information?
Okay, maybe you're calculating changes in entropy?
Yeah, so the information leakage, right, is not mutual information. It's what is the, like these are how many bits of information do I get about the website given a feature vector.
Okay, I thought you were quantifying that in terms of mutual information. So what, you're quantifying it in terms of entropy then? Or,
yeah.
Yeah, okay. So entropy still requires a prior distribution, right?
Correct.
Okay, how are you going to get prior distribution for the adversary?
Right, so that's one of the things which I didn't talk about, but we modeled different priors to show that this is an important feature, and you can incorporate whatever prior you like. The prior we used, I think that Shuai used for this slide was Zipfian. So the Alexa top 1 site had whatever probability, and then if you were site K, your probability was proportional to 1 over K.
Okay. Did you consider, so if you're not doing mutual information, I guess you wouldn't do channel capacity exactly, but something like channel capacity, but for entropy, where you take like the worst case? Is that something you could do?
I mean, yeah, so now you've got these likelihood functions, you can use them for whatever your favorite information theoretic or Bayesian analysis. Okay. Right. So I think that's really the cool part, is the density estimation.
Okay.
Other questions? We have time for one more question. I have one. Sorry. After that, we're done. You did some dimensionality reduction, right? When you gathered this stuff. Did you compare your dimensionality reduction with autoencoders, like adversarial autoencoders, variational ones, other
no
learning techniques?
So no, we didn't use any deep learning based dimension reductions. We did compare the approach that Shui used with PCA, and PCA was inferior.
Okay. Let's thank the speaker again.